Electric field due to an infinite charged plate. Here, I draw an annular region, and actually this is an infinite plate, and it is completely charged with the uniform charge density sigma. And to find the value of the electric field, I would choose this annular region and increase this R to 0 to infinity to cover whole plane. Sigma is the uniform charge density per area, so delta Q over delta area will be constant. To compute the electric field is rather complicated, so we introduced the potential, and the potential electrostatic potential is a scalar, very simple to compute in comparison with the direct computation of the electric field. We introduced the field point. To simplify our analysis, we choose the coordinate of x and y to be the same as the center of this annular region. So this is origin, and my coordinate for the field point is only carrying the z component only. Okay, and this annular region has the radius r, and the thickness, the width will be dr. Okay, now I can always make use of the fact this is the charge. Charge is divided by distance between the source and field point. The reason why I have chosen this annular region is that I can draw a cone. And everywhere on the annular region has the same distance from this point to there. And what is that distance? If I can draw a cone, I can always draw a right triangle, and this is a z and this is r. Now I know that capital R, the distance from the source to the field point, is completely determined by r squared plus z squared. Therefore, in this formula, what I replaced this for the area is annular region. This annular region is a band with the r, and the length is 2 pi r. So area of this annular region should be 2 pi r multiplied by dr. Now I substitute this guy in the denominator, and then this is 2 pi, 4 pi. I have 2 and epsilon 0 permittivity constant. Sigma is left, and r squared. Okay. By the way, I can multiply 2 divided by 2. And this one is the total differential of this guy. And that is the argument of the square root. This one is very simple. Because of this, we have additional factor of 2 in the denominator. And I know this is a total differential of square root. So now I have replaced this potential as a very simple one. And this is because it is total differential. I'm ready to integrate. What I can do is just this argument itself is the solution. What a simple problem is this. And if I consider the integral from 0 to infinity, subtracted 0 plus z squared, and we take the r to infinity. That is a potential. So we can notice that the potential, electrostatic potential, diverges to infinity. Don't worry too much because we are not interested in the Our potential is not the final destination, our final destination of the electric field, and this divergent behavior is just due to the fact that we have integrated over the very large space a collection of amount of charge very far away from this origin. They are summed, but eventually their contribution decays to zero as far as the electric field is concerned. So, because I have simplified this integral, and this is a constant factor and total differential, the answer is this. Now, we do not let this radius of the disk to the r goes to infinity before we compute the electric field. Let us compute the electric field first. The electric field calculation is simple. Just attach minus gradient. What is minus gradient? Minus derivative with respect to x, y, z. Now we know that this is capital R is constant and the only coordinate dependence is z. We do not have x and y contribution at all. That means at the center of disk, the electric field is along the normal direction, and tangent direction, they disappear because of the symmetry of the rotational symmetry of this system. Now what we have to do is take the ZA derivative. Now Z derivative is this, Z derivative is this. Okay, now we have obtained the electric field, and why don't we take the limit r goes to zero, r goes to infinity? In that case, even though it produced infinity in the electrostatic potential V, this one vanishes because it is now in the denominator. The only contribution comes from this, and what is that? That is z minus minus plus. So we have sigma over 2 epsilon 0 E3 hat z square root z squared. What is the square root of z squared? This is absolute value of z. Okay, so z divided by absolute z is equal to plus 1 if z is a positive, 0. 0, I don't know. We don't care much about the point of discontinuity, and we have minus 1 for z is negative. So we have a very large plate, that is a circular plate whose radius diverges to infinity, then electric field is being emitted from the plate in opposite direction. And we know that electric field at the center, we cannot compute this because it becomes 0 divided by 0. We assume this plate is very thin, so electric field diverges from the plate to outside. That is a very, very important. So infinite plate generates the electric field along the normal direction, whose magnitude is constant, but their directions are opposite.